Great. Okay. So I'm Trent. How it's going to be, how this evening will happen, like Carly mentioned, I'm going to give my talk in two parts, interspersed with others. So to start with, I'll actually be talking about music. Or there we go. AI. So I'm going to start with an introduction to AI. Then Greg will be talking about AI and legal. And then I'll be talking about AI DAOs, followed by Terra Zero and their super interesting application of DAOs with a sort of an AI element as well. So, but you know, we wanted foundations first. So introduction to AI by example. AI, artificial intelligence, how do you define it? There's actually a bunch of definitions. Not quite as contentious as definitions for blockchains, but still contentious. So the original definition, going back to Alan Turing, is a machine that can replicate human cognitive behavior, right? And this is best illustrated by the Turing test, where you have a room and people are sending messages back and forth to this entity in a room, which might be a human and might not be, and you try to determine whether or not it's a human based on the messages you send back and forth as pieces of paper. That was kind of the original idea, trying to mimic replicating human cognitive behavior. Now there's kind of two definitions that are a bit more pragmatic. One of them is performing a task that traditionally only a human could do, right? So an example is performing the game of Go, right? Like AlphaGo did in the last year, or chess, or other sorts of things. So at the level of a human. Another one is performing a task at a speed or accuracy or capacity not possible by a human at all. A good example with that is semiconductor computer chip design. You know, in our pockets we've got these phones, which inside there's chips of more than 1 billion transistors. And those chips were designed with only a team of 10 or 20 people. It's only possible because AI is actually connecting the dots. Those 10 people working with those billion transistors, connecting them together with the help of AI. And I'll get into some of that. So it's really, these days, AI, the goal isn't to try to mimic human behavior directly across the board. It's really about human level capacity or superhuman for specific tasks. Another way to think about it is, in the field of computer science, it's all the things that are still sufficiently a mystery that they haven't got their own field. That it's still a bit of magic, it's a non-numerical, etc. So it's a toolbox of ways to solve certain problems. And these problems, a good subset is classification, regression, knowledge extraction, optimization, and structural design or creativity. And in the next few slides, I'll talk a bit about how each of these are manifested. And then with that, if you do classification in just the right way, then you might have some business benefits, things like lower time to market, lower cost, higher yield, making new products possible. So what I'm going to do now is simply talk about each of these, classification and so on, with some very specific examples, and where possible, drawing on examples from my own career. So before I was in the blockchain world, I spent almost 2 decades in the world of AI and chip design. So I'll start with classification, which is one of the most popular applications. This is an example in 2 dimensions. So let's say that you are a bank and you accept credit cards and you want to decide whether or not you should give a credit card to someone who applies for it. So what you can do is you can say, okay, well, given past behavior of all the people who have had credit cards, and did they pay the bills, yes or no, right? Because if someone has a credit card and they never pay the bills, they're not a very good customer, right? You don't want them. So you have all these data points from before, and maybe on 2 dimensions of salary and age, okay? And so all the green is all the people who paid the bills before. You have data on that, and you have the red of people who weren't paying the bills. And you know, basically overall, what you want to try to do is get all the greens and not have the reds, right? So you want some sort of divider. And what a classifier does when you learn a classification model, it basically comes up with this dotted line in between of a distinction between when you should give a credit card or not. And so if a new person comes in and maybe they're, I don't know, super young and they have virtually 0 for a salary, so sorry all you high school students out there, you're probably not going to get a credit card according to this classifier, right? Unless you have a really awesomely paying paper route or something, I don't know, or some web business. But overall though, this is actually quite useful. And then how, specifically, what does this line look like? It can be one of many technologies under the hood. It can be simply a line, right? Y equals mx plus b in 2 dimensions. And that's called a linear classifier. There's a whole bunch of techniques like that, going back to perceptrons of the 50s. There's neural networks, there's deep learning, support vector machines, boosted trees, random forests, bag trees, all this. There's, throw a rock, you'll find a different technique. These days, deep learning is all the rage. It's a type of neural network that just happens to be extra big. But there's a lot of technology out there, and it's really the right tool for the right job. My very first task for National Defense Canada in the late 90s was actually doing classification, audio radar for tanks. So basically imagine you're, in these tanks there's actually 3 dudes. There's someone who is driving and looking at things outside there. There's, basically 3 dudes, and the third dude is actually sitting in the middle of the tank with headphones trying to listen to this audio radar signal that spans miles and miles and trying to figure out, is there another tank coming? Are there birds, etc.? And the government wanted to get rid of this third operator and replace it with a bot. And so my job was to see if this thing could be accurate. So it would listen to these signals and then say, yes, that's birds, or yes, that is another tank, etc. In the end, it wasn't accurate enough, but it was still a pretty cool summer job. So this is what I did for the late 90s. So that's classification, right? Yes or no, give a credit card, yes or no. Is it another tank, yes or no? Regression is, instead of a yes, no, it is actually coming up with a real valued output. So in this case, let's say that you're trying to predict job satisfaction as a function of age. And you've got all these data points. Someone who's young, maybe say 22 years old, and they're very satisfied. But maybe, by the time they hit 40, they're in midlife crisis and they're not very satisfied. But then they figure out some way to get happier again, right? So these are some data points. You can fit a model on this, like this. And then any new age coming in, you look here and you say, okay, on average, how satisfied will they be, right? So this is just a very simple regression problem. The whole idea is to fit this curve. This is one dimension, right? That's just one input, which is age. You can also have 2 inputs. So in this case, you've got age as one input and salary as one input. And it's coming up with some sort of model. In this case, what is the overall size of the credit card bill that they might have on average, right? So you try to fit some model. And once again, it could be a polynomial, a linear model, or something fancier like a neural network. And interestingly, if you want to go really crazy, you can even have 10,000 input dimensions. And this is actually how Google does search. They treat it as a regression problem. And what they do is they have the 10,000 most popular words in the English language, and then they measure the count of those words in any given page. And then basically they leverage that as a way to make search really fast. So this is actually searching for the word furry robot, if I recall correctly. And like that, right? Scary furry robot. So that's a regression in 10,000 dimensions. So I've talked about classification and regression. Another one that is less known, but I think is really cool, it's the idea of knowledge extraction. So basically trying to learn some new things, extract some knowledge in a way that helps to teach a human. In this case, this is circuit design. And you've got a circuit, this is an analog circuit, a Miller OTA to be precise. It amplifies signals basically. And with that, you can, what I did, this was some research I did in 2005. What analog engineers like to do is extract equations. What is the equation that describes gain as a function of all the different parameters of each of these transistors? How about phase margin and power consumption, all of these things? So I took this circuit and I ran a bunch of circuit simulations with something called SPICE. And then from those simulations, I invented an algorithm called caffeine, because I love coffee. And well, actually, I love caffeine, to be precise. Caffeine then would actually take these simulations and spit out equations like this. And an analog engineer can look at this and see, oh, look, gain is a function where it's minus 10.3 plus 7 e to the minus 5 divided by drain current of transistor 1 plus 1.87 times this equation here. They can look at this and get a feel for how the circuit behaves. There's lots of applications for this. For example, news feeds, right? What is the algorithm that Facebook might have for a news feed? You could take all that data, if you have lots of data about how it ranks the news feeds, and actually yank out and come up with a formula. So it's a way of giving transparency back to how regression algorithms are working. So this will have a much brighter future. It'll be pretty interesting to see. Another example is, let's say you have a massive data set. In this case, it's got a 5 by 5 dimensions. And You just want to understand what is the decision process. In this case, I'll be precise here. This was some work I did in 2008, and it would recommend what circuit topology you should use based on performance specs. So let's say, for fun, you're trying to buy a car, right? And if you say, my budget is greater than 100,000 euros or not, and then if it's greater than 100,000 euros, then you might say, do I want it to be fast or fuel efficient? And if you want it to be fast, maybe you choose a Ferrari. But if you want it to be fuel efficient, maybe you choose a Tesla or something, right? And basically, this is the same thing for circuits, and it comes down based on different performance specs, things like gain, bandwidth, and so on. And at the end of the day, it tells you which circuit you want to use. And so you can glance at this and do this. So it can be useful for deciding on cars, deciding on circuits. And interestingly, this is used all the time in the medical field. If you look at the study notes of any doctor who's studying, say, gastroenterology, like study of the gut, it is filled with these trees about how to diagnose and what steps to take next. So this is knowledge extraction. It basically goes from this to this automatically. Another big field of AI is optimization. And in optimization, the idea is you want to find the value of x, so in one dimension or higher, that maximizes f of x. So if this is the underlying functional mapping, which you don't know, you want to find this value of x here that gives you the maximum value of f of x. And you want to do it by having as few sample points as possible. So if you sample here, and it's expensive to sample, that's why. You sample here, you get this green dot. You sample here, you get this. And if you're smart about it, in just a small number of samples, maybe in this case 7 samples, you get the optimum. If you're not so smart about it, you might take 10,000 samples. And that could be expensive. For example, what if you're trying to maximize the click-through rate? You don't want to have 100,000 people come to your site just to have an optimal mapping. Ideally, you can do it in 10 or 50 visits. So this is the general idea of optimization. This is actually where I started my first company many years ago, where we were optimizing circuits like this. There would be, in this case, there's about 100 parameters. And the analog engineer is actually trying to say, what gives me the lowest power consumption? What gives me the highest gain, etc. Give me a circuit that balances all of these. And how do you juggle all 100 variables to give you high gain, low power? And it turns out a computer is very good at that, of course. So that's what we applied and did. Another example is taking that to the next level and actually giving visualizations of this all. So the user can slice and dice on a couple of dimensions and see sort of what the contours are at higher dimensions for extra insight. Keeping going, in the world of AI, this is something that is less known, but to me super interesting, super cool. And it's the idea of machine creativity. So machine creativity is computers doing things that were once considered creative. This is actually an antenna, and it looks like a bent paperclip, but it's literally an antenna. As you can see, it's quite small. And it was done by some friends of mine at NASA, basically as a way to help the rocket to communicate with home base. And this is actually the world's best antenna at doing this. And in fact, it did go up with rockets on the heels of the research that these guys did in 2004. And after that, Jason actually started a company called X5, and the company does this for a living for the last 10 years. So this is basically, it's super creative, it's super nonlinear. You would never expect a human to come up with this, but this is what the AI did. And in this case, it was actually doing simulated evolution, survival of the fittest antenna, if you will. Another one, it actually turns out to be really hard to design quantum computing algorithms if you're a human, because it's so crazy nonlinear and it's hard to sort of get all of it in your head at once. But this is something where if you evolve it, if you just have survival of the fittest quantum computing algorithm, it actually fits quite well. So my friend Lee Spector wrote a whole book on quantum computing algorithms, none of which he designed, all of which he got his computer to design for him. So, this is best-in-class quantum computing algorithms going back 10 years now even. Myself too, this is actually my PhD, where I was doing the same thing for circuits. And basically, it could give you circuits that were the optimal trade-off among any specs you wanted. In this case, it's the trade-off between gain, bandwidth, and power. So if you said, if you had a certain spec that you wanted in terms of the input voltage, and you wanted the optimal trade-off, then it would give you this. So every single dot along here is a different design. And all of these guys here follow this topology. But as you change one to the next, it's just changing a few of the parameters inside. But something interesting happens here. If you actually want to have a higher gain bandwidth than this, even just a bit, then you actually have to switch to a different topology right here. But it's actually taking 3x more power. And if you look at it, it kind of makes sense. Basically, if you're, in terms of power consumption, there's current flowing down this and current flowing down this. Whereas here, you've actually got current flowing down 4 channels. And that's why it actually takes way more power consumption. So you show this to an analog designer, and they're like, oh my god, this is really, really cool. So this is what I did in my PhD, basically helping analog designers design better chips. And it's basically creative as well. So it just helped push analog circuit design practice forward. Going back, my friend Greg, the NASA guy I mentioned before, he also, for fun, was doing jewelry design. So these are all actually pieces of jewelry that he got his AIs to design automatically. Once again, survival of the fittest. And he made it interactive. And how that works is, let's say that you like this, then you can click on it, and it will give you 20 variants of this necklace. And if you your favorite of those, it will give you 20 more variants. So just like Amazon has been Earth's largest bookstore for a while, my friend Greg basically created Earth's largest jewelry store by having billions and billions and billions of these designs. And then each one, when it gets to the end, it would just 3D manufacture it. So pretty exciting. So that's, oh yeah, I've got a couple more slides on machine creativity, because it is super cool and it will relate to some of the later stuff. This is art done via survival of the fittest, genetic programming. So it was the title image, but there's some really, really interesting art you can get. In this case, it was actually evolving a function, and then from that function, it would just render in 2 dimensions. Another way to do it is with deep learning. So deep learning is, like I mentioned, it's a neural network that happens to be really big. And a neural network is really sort of a graph of inputs. It's not, people talk about biological models of the brain and stuff. You don't need to get fancy that way. It's really just basically multiple inputs, and they all get summed up and then pass through some nonlinear functions. And this happens through a few layers, and you end up with results like this. So what's interesting, you pass in an input image, and then it passes through this crazy neural network, and you get stuff like this. And it kind of shows, this was trained on internet data, so almost everything uses cats and dogs as basis functions. He's got a bit of a dog head there. So, I mean, that's the takeaway from this slide, as cats are the new basis function. Yeah. Also, actually, riffing on the deep dreams, then people realized they could transfer styles. So you could take a photo of a cat and take a Van Gogh image, and then you could basically say, using just the right technique, you could actually end up with a cat in the style of Van Gogh. And what it's trying to do is, it starts off with a random image here, and then it tries to minimize the difference from the random image and the image of the cat in terms of the overall structure. And then it also tries to minimize the distance from this image to this one in terms of a local regional pattern, basically. And that's what it comes up with. And it's just really remarkable how it came up with this. So it's AI being creative. Now, one final field in AI, or subfield, is this idea of artificial general intelligence. And this is basically bots that run around in some sort of simulated environment. They have inputs, they have outputs, they maintain state, and then basically as they take in more inputs, they update their state, they perform actions, they actuate against the environment. And so it's actually a really cool way to test your AI creations. So for example, Microsoft has set it up where you can actually run your bots in Minecraft and play. And actually, in the last few months, there's been other movement like this too. I believe Blizzard is doing this with World of Warcraft and otherwise. So this is the idea of artificial general intelligence. It's trying to get closer to human-like behavior in a sense, but more for a restricted domain still, these environments. And this is a more nerdy slide, but I think it's really important. There's this field called control systems, which is really about a system that has a state, and it takes inputs, and it has outputs that it actuates against the world, and then it has a very precise way of modeling that. So it has its own model of the world. It uses that model to choose what to do next with the controller, and then it actuates against the world with a motor effector, right? And that actually updates the world, the external world, And then what happens is it has two models. It has this internal forward model that it updates based on the controller, and it has what it senses from the world, and it takes those two things together and updates its state of the world. So basically, the summary is you've got this system that has some sort of model of the world, right? It might be super, super rough and so on, and it's using that in order to actuate against the world, and it's sensing the world, and it just keeps looping, right? And this is the basics for AGI as well. So basically an AGI is essentially a control system, a feedback control system like this, that has these models and otherwise using some of the AI tools like neural networks and so on, right? This was also the key to these advances with things like AlphaGo for the game playing robots, where it's basically these dynamical systems. So yeah, that's AGI, Artificial General Intelligence. So to kind of summarize on AI, AI, in a mundane setting, it's a toolbox of ways to solve some of these problems: classification, regression, knowledge extraction, optimization, structural design, or creativity, with these benefits like I talked about, lower cost, etc. And it has all these subfields, right? Neural networks and deep learning is the most popular one right now, but there's machine learning, which is another big subset that's evolved a lot. I've talked about a lot in evolutionary computation, and within that too, evolutionary computation, this is the general field of survival of the fittest, and within that you have subfields like genetic programming, which is survival of the fittest computer programs, genetic algorithms, which is about bit string evolution, evolution strategies, and more. Then we have the field of swarm algorithms, right? The most famous is ant colony optimization, so you can actually have a whole bunch of dumb little ants running around, each with stupid rules. But with these stupid rules combined together in just the right way, then you have emergent effects on top, and they're really good at doing things like routing, pathfinding. So if you want to have optimal routing for your internet routers. Another popular one there is called particle swarm optimization. And in general, you can simulate a flock of birds, a swarm of bees, a colony of ants, whatever you want. It's all swarm algorithms. And then finally, AGI, which I talked about as well. And AI, though, it actually has, for those of you who have technical backgrounds, you might have noticed it actually has strong similarities, strong relations to many other fields, including statistics. And I really see machine learning is actually very much modern statistics. Within the field of machine learning, there's been big advances, for example, in linear regression, right? Traditional linear regression, you'd use least squares. You maybe would have, if you have 10 parameters, you'd need at least 11 samples to do a fit. These days, you could have 100 samples and 10 million dimensions and still come up with a model that isn't horrible, actually. So that's actually pretty interesting. It's also related to probability theory. Bayesian updates all this. Linear algebra in general, when you go beyond a matrix of which has 2 dimensions, a higher dimensional matrix is a tensor, right? And so now you can actually frame this all as a flow of tensors through a bunch of nonlinear functions, right? Call it TensorFlow, which is actually now the most popular deep learning library released by Google. Also, the field of nonlinear programming and optimization. This goes back to research in the 50s, 60s, 70s, especially out of Cornell and otherwise. Operations research, all of this. Control systems and cybernetics. This goes back to the 50s out of MIT, Norbert Wiener and these guys. Monte Carlo methods. This is basically random sampling, but there's a whole variety of things you can do there that are really interesting. And of course, the relation to philosophy and ethics, where there's friendly AIs and AI rights and so on. And Greg will actually talk about that in more detail. So AI basically, it's a rich field and a lot of things going on. It's not something that is, I think it's really important to emphasize. There's sort of the crazy Terminator view of the world, but there's actually much more mundane ways to think about it too. And it's incredibly useful and powerful. So I'll leave it at that as an intro to AI. And this is basically a baseline for the talks that follow. So now, without further ado, pass it off to Greg.